Hi everyone. I wanted to give you some examples to work from response questions for the AP Physics C Mechanics exam. So given that we're working with moments of inertia and torque and all of that, I thought I'd use some rotational mechanics for you. This is actually the third free response question from last year's AP exam. It's been released. You can find it online at AP College Board, along with its scoring rubric. So you can check it out. This is free, easy to find. So I wanted to go through this with you, though, to hopefully help you learn some of the things about what we look for in free response questions. So here we've got a uniform rod that has length L and mass M. It's allowed to pivot about the end. And the first part of this question is asking us to use calculus and integrate to derive rotational inertia for the rod about its end. And we want to be able to prove that it's actually L squared divided by 3. So I'm going to pull this away. We're going to start working. So first thing, anytime we're looking at the moment of inertia, we know that it's the integral of r squared with respect to mass. Okay? So we're going to have to be able to substitute in for dm. So we're going to, off to the side, I like to write my work. And first we're going to look at the breakdown of the mass to length ratio. And we use lambda for that. We're going to solve for m. So that means that lambda times L is equal to m. And now we're going to integrate that. So we're going to find dm. So we have theta dr is going to equal dm. So now we can actually substitute this into our integral so that we're only integrating over one variable. Okay? So now I is going to equal the definite integral from 0 to L, since that's the length of our rod, of our mass to length ratio times r squared dr. And so now we're just going to integrate that. This is a constant, so we don't have to worry about that. So we're going to raise the power of our r here, put it under, so 1/3, times lambda r cubed, evaluated from 0 to L. So now let's substitute in. We have 1/3. Oops. 1/3 times lambda L cubed minus 0. Obviously, the 0 goes away. And we can substitute back in for our lambda. So we get 1/3 times m over L times L cubed. So we can see that the L down at the bottom is going to cancel out, and this is going to become squared. And so we get 1/3 mL squared is equal to our moment of inertia, which is what the problem asked us to find for part A. So then we're going to look at this rod again. It's being held up here, and it's going to be allowed to swing down, and we want to know what the velocity is going to be of the free end of the rod at position B. And we need to keep our answers in terms of M and L and G and such figures like that. I'm going to use conservation of energy to do this because I find that to be easiest. Anytime you're going to use conservation of energy, momentum, anything like that, the best thing to do is to outright state it on the AP exam. A lot of times they'll give you a point for that. You can state it in a statement or in an equation. So I'm saying that my initial energy is going to equal my final energy. That means that my initial gravitational potential energy plus my initial kinetic energy is going to equal my final gravitational potential energy plus my final kinetic energy. Initially, then, my gravitational potential energy, I do not have any kinetic energy initially. And finally, I don't have any gravitational potential energy. My kinetic energy is rotational. So I'm going to put it in that form. And off to the side, we need to look at the initial height of the center of mass of the rod, because the top end's not moving at all and the bottom end is fully moving. So we're going to take kind of the average, if you want to think of it that way. Okay, so now I'm going to substitute in my M value here, G times L over 2. And I'm going to substitute in my I value that I found in part A, 1/3 ml squared. And then I need my rotational velocity, and I really need it in terms of V, since that's what I'm asking for. Well, we know from past units that V equals R times omega. And we know for this product R equals L. So we can substitute in and say V equals L omega, and V over L is equal to omega. So then I'm going to come back here and plug that in. Okay? So it's easy to see my M's are going to cancel out, and my L squareds on this side are going to cancel out. So on this side, I'm left with G L over 2. And on this side, I have 1/6 V squared. So now I just need to solve for V. Okay? All right. So that gets you a really good start there. Okay? The problem continues on and actually looks at things in terms of a lab and an experiment. Now we have an experiment is designed to test the validity of the expression found in Part B. The student uses rods of various lengths that have a uniform mass distribution. The student releases each of the rods from the horizontal position A and uses photo gates to measure the velocity of the free end at position B, and the data is recorded below. The question then continues and says, indicate below which quantities should be graphed to yield a straight line whose slope could be used to calculate a numerical value for the acceleration due to gravity. Okay? There's actually different answers you can have here, but they all fall on the same thing. If you are going to graph just the velocity, then you need to graph the square root of the length. If you're going to graph the length, it needs to be velocity squared. And whether whichever one you had on the horizontal or vertical axis actually didn't matter. They said all would yield a linear line. So I actually said, well, to me it seems like length would determine velocity, so I put that as the independent axis, and then I said I would need velocity squared on my y-axis. Okay? Felt like I didn't need any additional units. Okay. You're then asked to graph data and draw a straight line, so as well as find a line of best fit. So all you need to do is actually plot that out. Okay? The last question says use your straight line, determine an experimental value for G, and describe 2 ways in which the error effective resistance could be reduced. So I'm going to go ahead and show you part I. So for my part I said, well, I know that the slope of my line, M, is equal to V squared over L. And then from part B, I also know that V squared is equal to 3G times L. And so then I plugged in what did I do? Oh, that's right. Okay. So then I substituted in for my V squared here and said that M is equal to 3GL divided by L. So M is equal to 3G, and so M over 3 equals G. So that means that G is equal to 1/3 of my slope value. So if you find slope value, you just divide by 3 and then you'd finish the problem. To decrease air resistance effects, you can have more dense or massive rods. Shorter rods, you could do the experiment in a vacuum, make the shape of the rods more aerodynamic, and that was pretty straightforward. So hope this gives you a little taste of a free response question, and let me know if you have anything else you want to see.